a lot of talents that won't earn me money. So, all right, so we're going to use implicit differentiation to derive the differentiation formulas for the inverse trig function. It sounds like it's redundant, derive the differentiation formulas, but derive in this context means generate, like build the differentiation formulas. So it's kind of like an alternative way to think about these things rather than just rote memorization. But you may look at it and say, okay, well, that's all really great stuff. I'm just going to memorize the formulas. And that's perfectly within your right. I just want to make sure that I at least show you at some point where these formulas are coming from. And that's all part of the fun. All right. So we need the derivative of the arc sine of u. All right. The result of arc sine of u should be some angle that we call theta. So this is really asking what d theta dx is. So the derivative of some angle theta with respect to x. Okay, so let's just kind of play that out for a second. So let me, off on the side here, say that theta is equal to the arc sine of u. All right. Now, this poses a pretty significant issue, because if I want to take the derivative of this, it would require me to know what the arc sine of u's derivative is. But I don't, so I can't do it that way. What I'm going to do instead is I'm going to take the sine of both sides. Right? So it's really the same as saying the sine of theta equals the sine of the arc sine of u. Right? The whole right-hand side boils down to just a u. Right? Because the sine and the arc sine are inverses of one another. They cancel out to whatever the angle, or in this case, the ratio would be. All right? So then I have a relation that's a little bit more, we'll call it user-friendly. I have u equals, well, I'll write it as u equals the sine of theta. Cancel each other to whatever is contained within the arc sine, in this case u. All right, so what I have to do is find the derivative of this, because I knew I had to take the derivative at some point, but I'd rather work with this than the other thing. So I'm going to take the derivative of u with respect to theta, and that would be equal to derivative of sine is cosine. All right, so that's something. We're not there yet, but it's something. Right. I need d theta dx, because again, this whole thing is theta. So d theta dx. I have du d theta. So it's really not close to what I need, but I can do a few things to get it closer. First, I'm going to write that cosine over a 1, and then take the reciprocal and that's going to give me a d theta du equals 1 over the cosine of theta. Now you could write that as secant, but let's not for now. All right, you'll see where it's going in a minute. So based off of this, and this really connects to what we were talking about last class, this arc sine of u, again, it's an angle. That angle is related to some triangle. It's the reference angle of some triangle. The ratio in there is u, but we think of that as u over 1. The sine ratio is opposite over hypotenuse. So my opposite side is u, and my hypotenuse is equal to 1. Now cosine is the ratio of adjacent to hypotenuse. All right, so I need to come up with the adjacent side. I need this guy here. All right, so by the Pythagorean theorem, that would be the square root of 1 minus u squared. All right, so if from this I'm just trying to pull out a cosine of theta, it would be the adjacent over the hypotenuse, which would be the root of 1 minus u squared over 1, which is just the root of 1 minus u squared. So now I have a substitution. So the root of 1 minus u squared can replace the cosine of theta here. Okay? And if you know anything about what the rules are, you can see that that's almost it. Okay? Because this would become 1 over the square root of 1 minus u squared. All right? So let me rewrite that real quick. We have d theta du. I'm actually going to leave a little space after that before the equal sign. Is equal to root of 1 minus u squared. But I need my derivative to be in terms of x. All right? So I need, again, this is the same as saying d theta dx. I have a d theta du. I need that to become a d theta dx. So I have to multiply it by something in order to make that happen. And if I multiply it by something on one side, I have to multiply it by the same something on the other side. All right? So I need the du to go away, so I'm going to multiply it by a du, and I need to introduce a dx on the bottom, so I'm going to divide by a dx. So multiplying by du dx on both sides would give us our full-blown, ready to rock and roll derivative formula of 1 over 1 minus u squared times du dx. That was fun. We'll do another one in a second, just so you get a second look at it. But yeah, because there's a lot of moving parts there, a lot of color too. Very nice to look at. But yeah, it's the origin story, and it's also this whole triangle thing. It's going to lead us into trig substitutions, which is the focus of tonight's class. So, so having a sense of going from algebraic form of a trig expression to the trig form of that expression, that's going to be an important thing to realize. So I now know my Arctan rule for the derivative is 1 over the root of 1 minus u squared times du dx. Okay. As it turns out, cofunctions are just negations. So once I find arcsine, I know arccosine is just going to be the negation of that. So I'm going to be a little lazy. Clone. And then just pop in a little negative sign. Right about there. And let me see about making this smaller. Just conserve some space. I guess I could do it here too. Alright, see, that's where I run into trouble. Maybe I'll just do these guys. Oh, son of a gun. Oh, that's the worst. You know what? That's what I'll do. I got it. I got it all figured out. I'm not really sure why I'm recording any of this, but I'm doing it for some reason. Oh, this is so painful. Like, the whole universe is hitting next on this video right now. They're not hitting the thumbs up icon. I think I could live with everything else as is. Okay, it's close enough. I just wanted to squeeze a little bit more room out of that. All right. So Arctan. It's gonna have the same general process. So if you're a little iffy on the first example, second one is going to be helpful at a minimum. All right. So again, we're thinking of this as some angle theta. And so this whole thing we think of as d theta dx. I only make a note and make mention of that because I want to have an eye on what it is I'm looking for. What's my end game? What's my final goal here? So I'm going to jot somewhere that theta is equal to the arctangent of x, u I mean. Now, instead of showing that I'm going to actually take the tangent of both sides and then simplify, I'm just going to go right to it and say that this is going to correspond to u equals the tangent of theta. All right, so I am taking the tangent of both sides, but I'm not showing that I'm taking the tangent of both sides. Then I take the derivative. du d theta would be equal to secant squared theta. I think of that secant squared theta as being over 1. Eventually, again, I want a d theta dx. So I want d theta on top. So I'm going to write this as d theta du. And the last one, like I said, 1 over cosine, you can make that secant. Here, secant, when you reciprocate, when you make it 1 over secant squared, you can make it cosine squared. Okay? Or you can leave it as is. I'm just doing it this way because most people in the past have looked at me like I had 5 heads when I wrote cosine squared. They're like, where did that come from? So, I mean, you shouldn't be looking at me as if I have 5 heads when I write that, but it happens. So, anyway, try to make a reasonable looking line. Triangle. Theta. Again, we have a u here, which again is u over 1, but it's a tangent ratio, which is opposite over adjacent. So the opposite side is u, the adjacent is 1, the hypotenuse would then be the square root of 1 plus u squared. Or u squared plus 1, it doesn't matter, under the radical. As traditionally they write it as 1 plus u squared. Okay, so I can pull out the secant ratio from this, or I can go to cosine squared, but I'll do it as a secant. Secant of theta is equal to hypotenuse over adjacent. It's reciprocal of cosine. Hypotenuse is the square root of 1 plus u. Oh, it's going off the clip. Dang it. 1 plus u squared. But I need secant squared, so let me square both sides. And so now I can do my direct substitution and replace the secant squared with a 1 plus u squared. So d theta du leave a little space, just like we did for the last one, is equal to 1 over 1 plus u squared. But again, I want d theta dx, so I'm going to multiply both sides by du dx. Alright, and again, we multiply that by du dx so that the du's cancel, and we introduce a dx, giving us d theta dx, which is what we're looking for, is equal to 1 over 1 plus u squared times du dx. And that's our arctangent rule. Just going to tuck it in here. So the second one down. And the arc cotangent has the same relationship with tangent that arc cosine had with sine. I really shouldn't need to just clone a negative sign, but I'm doing it anyway. Alright. So then it's, okay, well, what about our secant? I want you to be able to play around with that. So I'll just give you the arc secant. I shouldn't have zoomed out. Alright, well, whatever. I'll just write small. 1 over the absolute value, the square root of u squared minus 1 times du dx. You got it. It's an attempt at making a power of 2 here.
No, I really didn't see that was a joke.
No, I mean it's pretty terrible. It's pretty awful. I'll allow that. Yeah, it's 1 over the absolute value of u times the square root of u squared minus 1. All right. The absolute value of u is the weird part. You kind of look at what we just did in those derivations, and you say, well, how are we getting an absolute value out of that? Well, the short answer is because the u is the hypotenuse, and since we're assuming that the hypotenuse is a vector quantity, and that vector is the result of the Pythagorean theorem, we're going to assume that it has to always be positive, although there's reasons for why a vector would be negative, but we make that assumption in this case. Otherwise, we'd have to take into account positive and negative hypotenuses in every single situation, and it's just overwhelming, right? And it doesn't give us any additional answers, no additional solutions, because it's basically saying that if you had some distance out from the origin, some vector, that vector could be pointed in the positive direction or the negative direction. And so what these signs are really telling us, or the signs related to the u, the length of the hypotenuse, is whether it's going in the positive direction, or if you're looking at something that would be going in the reverse direction. Right? In this context, that's how the positive and negatives are defined. But really, what does it amount to? The same length, right? In either instance. Doesn't matter if I start here and draw it that way, or start here, draw it that way, or start here and draw it that way. It's still going to be the same length. All right. Now that's different from vector notation, vector spaces, and things like that from physics, and also in Calc 3. There's a different way of thinking about it. But that's the rationale there for the absolute. But you'll see when you try that problem. I don't think I put a star on it, so let me do that. right? So the examples below, well, they're not that bad at all if you're just applying a rule. Because I have an arc-sine rule right here. So this would be my u. So I'd be looking at, all right, I think I can handle this. 1 over the square root of 1 minus the u, 2x, squared, times du dx. So the derivative of that u would be just a 2. Yeah, that's it. That's it. The second, third problems are along the same lines. The fourth one's got a little extra juice to it. Yeah, I'll do it. I'll do it with you now. It's got a little chain rule action going on because it's cosine of this. So I'd have to address that first. So it's the derivative of cosine, which is negative sine, of the inner function, which would be arc sine 3x. And I would take the derivative of the arc sine 3x, which is basically a repeat of the first example with a 3 instead of a 2. So I could just rewrite what I have there. You can consolidate it if you want, but I'll leave it separate. I really did reproduce it. So it's essentially the same idea, except really two things. One, I have an outer function that I need to take the derivative of, so I got that taken care of. And then an inner function is related to this. But then the second component that makes it a little spicier is that there's more you can do here. All right. So these two, you have two inverse functions that are composed. So I'm looking at the sine and the arc sine canceling out. So I'm going to hang on to the negative, and I'm going to hang on to the 3x, because that's all that emerges from that. The other part can consolidate to 3 over the root of 1 minus 9x squared. And then when you finally clean it up, you get negative 9x over 1 minus 9x squared. All right. So just think in reverse for a second. If I gave you this problem here as an integral, you're probably not thinking that its antiderivative is going to be anything remotely like this. And actually, in this case, if I were finding the antiderivative, I would simply use substitution. Right? So u would be equal to, I would go 9x squared, and use that to cancel out some things. And it would actually clean up kind of not bad. Actually, I would even use 1 minus 9x squared. It would clean up pretty nicely into an algebraic expression. But that algebraic expression would be equivalent to this. So this is a trigonometric representation of something that's algebraic. It's actually a radical function, right? A conic section specifically. The sine and the arc sine cancel each other out. So those are gone. All I have left is this and this. But that's a good point to bring up, because if this outer function was anything other than cosine, then you wouldn't have that cancellation. You'd still have something that's algebraic as a final answer, but you wouldn't be able to simply just cancel it out. If you have something like tangent of the arc sine of 3x, what do you do then? You draw a triangle, right? That's why I keep drawing those triangles, because they're that important. Right? We're going to do more with that as we go forward. Okay. And meh. And meh. Yeah. Oh, it goes super quick. I'll put for this one I'll probably just post an answer key though, because it's like super good. Another typo for somebody. Let me see. This one, number 5 and number 6, really, I think those I think are the juicier ones because they involve quotient rule and product rule, right? But the other ones they kind of work pretty much the way they did on the previous page. So 44.